Hello everyone, my name is Yuki Lavinia. I'm going to talk about challenges in using machine learning for networking research, how to label if you must. As the title suggests, the main subject of my talk is about labeling networking datasets to train machine learning models. Machine learning has been a popular technique that is widely adopted. The fuel that drives machine learning is data, especially labeled training data. Given this context, here is the outline for this talk. I will discuss the challenges, our proposed contributions to address these challenges, then I will briefly go over the building blocks that make up our solutions, then dive deeper into our framework pipeline. After that, I will talk about evaluation and finally conclusion and future work. And with that, let's start with the challenges in using machine learning in networking. The first challenge is the lack of labeled networking data. Generally, this is caused by the difficulty in labeling data at scale, which in turn is due to the lack of agreement on features that describe events of interest. For example, what should be the features of good data or features of bad data? Another cause of the difficulty in labeling is the diverse nature of the networking data, which are collected in various manners and comes in different time granularities, locations, and conditions, making them harder to label at scale. In addition to that, the human cost of labeling is also high, since creating labels for network data requires domain expertise, and these experts are limited in number while there is a large amount of data to label. Next, the second challenge is the privacy issue that surrounds network data. Because of this privacy issue, researchers have generally taken the safest approach to prevent even a possibility of privacy leaks, which prevents the sharing of raw or labeled data with third-party researchers, and also the sharing of machine learning artifacts, such as learning models. All of these are creating roadblocks in using machine learning in a collaborative setting. Finally, the third challenge is hidden biases in data, which is inherent in machine learning and is made more complicated by the fuzzy nature of the network data. These hidden biases can result in labeled training data that lack representation of certain minority group, creating a model that does not generalize well. Now we would like to introduce our contributions. To address the lack of labeled networking data, we propose a solution that creates label at scale in a programmable fashion and at low human cost. To address the privacy concern, we propose a solution that allows sharing only the learning algorithms, but not the raw data or the learning models. Finally, to address hidden biases in data, we propose the use of multitask learning. Multitask learning is a machine learning technique that focuses on more than one task at the same time. As each task has its own patterns, a model that learns multiple tasks at the same time is able to form a more generalized representation of the data, resulting in bias reduction. In this paper, we will discuss our first and second contributions, and we will leave the implementation of multitask learning for future work. With that being said, we would like to introduce eMERGE, a framework to democratize the use of machine learning for networking research. eMERGE captures the solutions that we listed here to address all those challenges. Our current version of eMERGE presents two key contributions. First, eMERGE creates high-quality data labels at scale in a programmable fashion and at low human labor cost. Second, eMERGE promotes privacy-preserving collaboration between different research groups to advance machine learning and networking research. Next, I will discuss the building blocks of eMERGE. The first building block is weak supervision, a learning technique that takes a small set of low-quality labeled data, which is a subset of an unlabeled data set, to label the rest of the data set and train them in a supervised setting. In 2016, a paradigm called data programming, which operates in a weak supervised setting, was introduced. In data programming, domain experts write programs that categorize data into classes, and these programs are called labeling functions. Learning from the labeling functions, the model then produces probabilistic labels. In 2017, Snorkel was introduced as a framework that implements data programming. The limitations of Snorkel, however, first is that it is not specific to networking. The second limitation is that it has scalability issue. This is because as the data amount and diversity increase, the task of studying the data to find heuristics for labeling functions become labor intensive, which increases the human labor cost. SNUBA was then introduced to address the scalability issue. In SNUBA, users label a subset of data, and then using simple classifiers, it learns to assign labels to the rest of the data, creating probabilistic labels. The limitation of SNUBA is that it is also not specific to networking, which brings us to the next building block, no more noise. No more noise takes inspiration from data programming and Snorkel to solve networking problem, which is to remove noise and latency measurements. Its limitation is that it is not scalable, especially when the network data increase in number and diversity. Having seen the building blocks of eMERGE, here we see the eMERGE architecture. Recall that the goals of eMERGE are to create high-quality labels at scale and at low cost, and also to promote privacy-preserving collaboration. To accomplish the first goal, eMERGE takes labeled data and unlabeled data as input, and then pre-process the data. The result is RTT values that are ordered according to the timestamp. Next, eMERGE calculates the features of the data, creates combination matrices of these features, and passes them to SNUBA. The simple classifiers in SNUBA learn from these features to produce probabilistic labels for the previously unlabeled data. To assess the label quality, eMERGE uses the labeled data to train LSTM models. Next, to satisfy the second goal, eMERGE provides a platform to share learning algorithms, which are the labeling functions. To accomplish that, eMERGE takes labeling functions and unlabeled data as input, and then using the generative model that is embedded in the no more noise component, eMERGE learns from the labeling functions and creates probabilistic labels. Note that there is also an optional connection between SNUBA and the generative model in no more noise. Now that we have shown our framework, let's turn to the evaluation portion of this talk. In the next few slides, I will go over the datasets, methodology, which includes 2 experiments, results, and future work. Now let's talk about our datasets. We use the traceroute data from K2Arc. Our data consists of 28 source destination pairs and amount to around 75,000 RTT measurements. Moving on to the methodology. For the first experiment, we wanted to address the problem of the lack of labeled data. So our goal is to demonstrate that eMERGE can create high-quality labels at scale in a programmable fashion and at low human cost. To accomplish this goal, we developed a task to differentiate good data from noise. In this task, we use 2 different types of method to label data. The first approach is what we call the naive method, where we use simple statistical heuristics like mean plus standard deviation, or outlier detection, or anomaly detection. The second approach to label is using eMERGE. Using these 2 methods in labeling, we will evaluate the quality of the training labels produced by eMERGE compared to those produced by the naive methods. So both methods of labeling will go through data preprocessing. While the naive method pipeline will get training labels right away, the eMERGE pipeline will calculate feature combination from the preprocessed data to produce probabilistic labels. And then we will use these labels to train LSTM models to generate the F1 scores. Note that we will evaluate the LSTM performance on the validation and test sets, which will be given ground truth labels. Finally, we will compare the F1 scores to assess the quality of the labels. The higher the F1 score, the higher the label quality. We want to know if eMERGE could produce labels with higher quality than the naive methods. In the next slide, we will focus on the details of the data preprocessing step and the feature combination step. In data preprocessing, first, we analyze the data to determine a threshold that separates good data from noise. Noise, in this case, refers to values that do not represent the actual network conditions. Second, we record a threshold, values for the naive methods. Third, we oversample the noisy data. Fourth, we divide the data. We take 500 data points for the test set, and from the remaining data, we take 20% for validation and 80% for training. Fifth, we label the validation and the test sets. We label -1 as noise and +1 as good. Next, for feature combination, we calculate 8 statistical features, which are the following features. Now, since we have discussed the details of label generation and F1 score comparison in the previous slide, we are ready to see the results of experiment 1. In this plot, the y-axis shows the labeling methods that were used to train the LSTM models. From top to bottom, we see that the first 9 are the naive methods, while the last one is emerge. The x-axis shows the F1 score that each method generates. From this result, with 0.996, emerge outperforms the naive methods by up to 6.7%. Compared to the naive methods that use simple heuristics to label, emerge learned from the data to pick up the unique characteristics. And because of that, emerge was able to assign more accurate labels, which improved the label quality. So here, we accomplish our goal to demonstrate that emerge can create high quality labels at scale and at low human cost. Now that we are done with experiment 1, let's talk about experiment 2. In this experiment, we want to address the privacy issue that can impede fruitful collaboration. Our goal is to demonstrate that emerge promotes collaboration to advance machine learning and networking research by sharing only the learning algorithms. To accomplish this goal, we developed a task to show how researchers from different groups can use emerge to collaborate. For this, we consider a scenario where 4 different research groups are collaborating to improve label quality, which is done by sharing the learning algorithms and, in this case, labeling functions. So each group writes its own labeling functions. In this experiment, we used the familiar heuristics from the naive methods in experiment 1 to write our labeling functions. We used mu, EE, LOF, and mu plus 2 sigma. Our next step is to combine labeling functions to generate probabilistic labels, then train LSTM models using the labels, and evaluate the label quality by comparing the F1 scores of each combination. We want to know if the collaboration platform that emerge provides would improve label quality. So now here are the results of experiment 2. We are showing the F1 scores associated with 1 labeling function, 2, 3, and 4 labeling functions. From the tables, we see that combining 2 labeling functions sometimes increases the F1 score, as in the case of combining EE and LOF, which increases the individual scores to 0.890. However, we also see that combining 2 labeling functions can drag down the higher F1 score of the 2, as in the case of combining mu and EE, which reduces EE's F1 score to 0.720. Combining 3 labeling functions can also drag down the higher F1 score, where the combination reduces LOF score from 0.836 to 0.733. However, when we combined all labeling functions, we see a score of 0.914, which is higher than each individual score. This is because emerge learned from the agreement and the disagreement of labeling functions. So the more labeling functions, the more learning opportunity for emerge, and the higher the label quality that emerge produced. With this result, we demonstrated that the collaboration platform that emerge provides can advance machine learning and networking research while preserving privacy, which satisfies our second goal. Let's move to the hyperparameter setup. For our experiments, we use the following hyperparameter value options. Note that different data sets can have different hyperparameter values. Finally, to conclude, in this paper, we proposed solutions to address the lack of labeled network data, the privacy concern in data, and the hidden biases in data. We have demonstrated that emerge accomplished the following tasks. First, emerge was able to create high-quality labels at scale and at low human labor cost. We have shown that the F1 score for emerge is higher than those of the naive methods. Second, emerge promotes privacy-preserving collaboration that advances machine learning and networking research. We have shown that the combination of shared labeling functions was able to improve label quality. Finally, we propose the use of multitask learning to reduce bias. For our future work, besides implementing multitask learning, we consider using other networking data types to assess the versatility of emerge, and then we also consider using different events of interest for emerge to detect. Lastly, our code is available at this link. We want to say special thanks to NSF for funding the project. Thank you for listening, and now we welcome questions.